In the last lecture, we had derived the mass and energy conservation equations. The mass conservation equation for the concentration field and the energy conservation equation for the temperature field. The mass conservation equation was of the form divergence of the velocity times the concentration is equal to minus the divergence of the flux. In this equation, the concentration is a scalar, the velocity and the flux are vectors, and the flux is in turn related to the concentration field minus d times the gradient of the concentration field, where d is the diffusion coefficient. So, in this equation, the concentration is a scalar, the velocity and the flux are vectors. The velocity vector in a Cartesian coordinate system can be written as Vx Ex plus Vy Ey plus Vz Ez in a Cartesian coordinate system which contains x, y and z as the 3 axes. Similarly, the flux is written as Jx Ex plus Jy Ey plus Jz Ez, where Jx, Jy, Jz are the components, and the gradient of the concentration field is a vector partial c by partial x plus Ey partial c by partial y plus Ez, where Ex, Ey, Ez are the unit vectors in the 3 coordinate directions. And in a different coordinate system, a spherical coordinate system for example, where the 3 coordinates are the radius r, the distance of a point from the origin, the angle theta made by the position vector with respect to the z axis referred to as the azimuthal angle, and the angle that the projection of this makes with respect to the x in the projection of the radius vector in the xy plane makes with respect to the x axis. It is called the meridional angle phi. So, in this case there are r, theta and phi. And you can write these operators in a similar manner in this as well. So, the gradient of the concentration will be equal to Er times partial c by partial r plus E theta by r, partial c by partial theta plus E phi by r sin theta, partial c by partial phi. That is the gradient operator, where these terms here are the scale factors which are required to convert the increment in angle into an increment in distance. And if the diffusion coefficient is a constant, the conservation equation just becomes d del square c. And this operator, the divergence of the velocity or the flux, let us say, in a Cartesian coordinate system is equal to partial Jx by partial x plus partial Jy by partial y plus partial Jz by partial z. And the same thing in a spherical coordinate system can be written as del dot j is equal to 1 by r square d by dr of r square jr plus 1 by r square 1 by r sin theta, I am sorry, 1 by r sin theta, partial by partial theta of sin theta j theta plus 1 by r sin theta partial j phi by partial phi. where Jr, J theta and J phi are the components of the flux along the 3 coordinate directions at this location. Er is along the direction of increasing r, E theta is along the direction of increasing theta, and E phi is along the direction of increasing phi. Okay. So, these are the unit vectors perpendicular to each other in a spherical coordinate system, and the Laplacian in a Cartesian coordinate system is partial square c by partial x square plus partial square c by partial y square plus partial square c by partial z square. And in a spherical coordinate system, this is 1 by r square d by dr r square partial c by partial r plus 1 by r square sin theta partial c by partial theta plus partial square c by partial phi square. Okay, so those are the, so basically these operators, the conservation equation expressed in terms of the operators is exactly the same in any coordinate system, the gradient, divergence and Laplacian operators. What changes is the definition of the operators themselves in the different coordinate systems. Okay. So, this is as far as the concentration field is concerned. The the energy conservation equation has a very similar form. Okay. Partial by partial T of rho Cpt plus the divergence of the velocity times rho Cpt is equal to minus the divergence of the heat flux vector, okay, where the heat flux vector is defined as minus k times the gradient of the temperature field, just as the mass flux vector was defined as minus the diffusion coefficient times the gradient of the concentration field. If the properties are independent, if the properties are invariant, the density, the specific heat and the thermal conductivity are invariant, then this can be written as rho Cp into partial T by partial T plus divergence of V times T is equal to minus the divergence of K grad T. Okay. The divergence of K times grad T is a vector, flux is a vector in a manner similar to the mass flux. Okay. And if further the thermal conductivity is also a constant, we can divide throughout by rho times Cp and write the equation as partial T by partial T plus divergence of the velocity times T is equal to, I am sorry, there should be a positive sign here, okay. Should be a positive sign here because I have a negative sign here for the flux and the negative sign here for the equation for the flux, the constitutive relation, that is Fourier's law for heat conduction. And here I get K by rho Cp del square T, and this term here is the thermal diffusivity alpha, okay, the thermal diffusivity which we will call alpha in this course. Okay. So, that is a summary of the mass and energy conservation equations. Okay. Then I had derived for you the mass conservation equation for the total fluid density. For the total fluid density, that is partial rho by partial T plus divergence of rho times V is equal to 0. Okay. This is for the total fluid mass, this is not for a particular component. Okay. So, the condition that total mass has to be conserved, right. Mass can be converted from one form to the other, but the total mass has to be conserved, except in the exceptional cases when you have conversion between mass and energy, okay, in nuclear reactions and so on. So long as you do not have conversion between mass and energy, total mass has to be conserved, and therefore, this gives us partial rho by partial T plus divergence of rho times V is equal to 0. Okay. and I had written this in different forms. Okay. One is to write this as in terms of v dot grad rho plus rho del dot v is equal to 0. And if you recall, we had defined this as the substantial derivative. That is the derivative in a reference frame that is moving with the fluid velocity. That is, if a point was at the location x, y, z, t, a material point, a fluid element, then it moves to a nearby location in after a time t plus delta t. That location is given by x plus Vx delta t, y plus Vy delta t, z plus Vz delta t, comma t plus delta t. This is a moving fluid element, not a static point in space. It moves with velocity v. Therefore, the location after a time delta t is going to be the position at time t plus delta t times the velocity. In this reference frame, the change in the concentration is given by this substantial derivative d rho by dt, which is partial rho by partial t plus v dot grad rho. So, plus rho del dot v is equal to 0. And if the density is a constant, then we just get that the divergence of velocity is equal to 0. For incompressible flow. The density is a constant for an incompressible flow. That is rho is equal to a constant. And we had also looked at, in case the divergence of velocity is equal to 0 for an incompressible flow, right, and the flow is 2 dimensional, we can express the flow in terms of a stream function in such a way that the mass conservation equation is identically satisfied. So, if you had only a 2 dimensional flow, del dot v is equal to 0 reduces to partial Vx by partial x plus partial Vy by partial y is equal to 0 if x and y are the only 2 components for a 2 dimensional flow. And in this case, I can express the velocity components as Vx is equal to partial psi by partial y and Vy is equal to minus partial psi by partial x. And if you substitute this into the mass conservation equation, you will find that it is identically satisfied. So, you can express it in terms of the stream function. And I had also given you another interpretation of the stream function in the xy coordinate system. If you have 2 points A and B, and I have a velocity vector, I have the unit normal to this path between these 2 points. In 3 dimensions it would be a surface, in 2 dimensions it is just a line. Then I showed you that the difference in the stream function between these 2 points is equal to integral over this path dx, integral over this path dx, dotted with the velocity vector itself, over this path ds of, I should be careful here, over this path ds of between these 2 points of n dot the velocity. So, that is the normal component of the velocity. So, if the velocity has some particular direction, you dot the velocity with the unit normal n, this is the velocity vector, Okay, v dot n, that is the normal component of the velocity to the surface integrated over the surface, gives you the total flow rate between these 2 points. Okay, so that is the interpretation of the stream function. And I had also talked about the stream function in a cylindrical and a spherical coordinate system. In a cylindrical coordinate system, if there is variation only in the r and the phi directions, okay, so if I had a 2-dimensional polar coordinate system, okay, r and angle phi, okay, and if there is variation only in the polar coordinates, then the mass conservation equation becomes 1 by r d by dr of r v r plus 1 by r partial v phi by partial phi equal to 0. And I can define V r is equal to 1 by r times partial of the stream function with respect to phi, and V phi is equal to minus partial psi by partial r, and these two equations identically satisfy the mass conservation equation. That is, these two substitutions for any value of psi will satisfy this mass conservation equation. Okay. And similarly, in a spherical coordinate system that is axisymmetric, that is, there is no variation in the phi direction, the equation becomes 1 by r square d by dr of r square v r plus 1 by r sin theta is equal to 0, and the velocity components can be written as 1 by r square sin theta partial psi by partial theta, and v theta is equal to minus 1 by r sin theta partial psi by partial r. Okay. So, those are the expressions for the stream function. So, that is where we were in the last few lectures. Okay. Now, we will go on to the momentum conservation equation. Okay. This is also called the Navier-Stokes momentum conservation equation. In the mass conservation equation, we had a constitutive relation for the mass flux J, okay, as minus d times the gradient of the concentration field. Okay. Mass is a scalar, therefore, the mass flux is a vector. Okay. So, in 3-dimensional space, for example, this mass flux gives you the mass transported at a surface per unit area per unit time along the direction perpendicular to the surface. Okay. So, therefore, J dot n. Okay. So, J is a vector defined at each point. Okay. The gradient of the concentration field, negative of the gradient of the concentration field, because mass is transported from higher concentration to lower concentration, whereas the gradient is from lower to higher. Okay. So, therefore, you have a negative sign. Okay. So, at any point this is uniquely defined. The gradient is a uniquely defined vector at each point in the fluid. Okay, the gradient of the concentration is a uniquely defined vector at each point in the fluid. Okay. The mass transported per unit area per unit time at a surface with unit normal n, okay, is given by the component of the flux along that direction, okay, J dot n times delta s, where delta s is the surface area, okay, is the surface area. Okay. So, J dot n, okay, J is the flux per unit area per unit time. It is a vector that is defined uniquely at each point in the flow. J dot n is the component perpendicular to the surface. It is only the component perpendicular to the surface that transports mass across the surface. Okay. Okay. So, the mass transported per per unit time is per unit time, okay, is equal to j times delta s, j dot n times delta s at a surface. So, the mass transported across the surface depends upon the orientation of the surface, it depends upon j dot n. However, the flux itself is independent of the orientation of the surface, it is uniquely defined at each point. And as you know, the maximum variation in the concentration field is along the gradient direction. Okay. So, therefore, the transport of mass is per unit area per unit time is a maximum along the direction of the gradient itself, because flux is a vector at this point. Okay. So, flux is some vector at this point, j dot n is the mass transported in the direction of the unit normal. This will be a maximum when j and n are in the same direction, okay, and it will be 0 when they are perpendicular to each other, that is, any flux that is parallel to the surface does not transport mass across the surface. Okay. So, for a scalar field such as the concentration field, the flux, okay, the rate of transport of the scalar field, okay, per unit area per unit time across that surface, okay, that flux is a vector. Okay. In momentum conservation equation, we are looking at the rate of change of momentum. Okay. We are looking at the flux of momentum. Okay. Note that momentum itself is a vector. Okay. The momentum itself is a vector, and therefore, the flux of momentum has to have two directions in it. Okay. Okay. By analogy, the flux of mass has only one direction, the direction in which mass is transported, because mass itself is a scalar. Okay. Similarly, energy transport, the rate of energy transport, the flux at a point has only one direction, the direction along which heat is transported. Okay. In the case of momentum, there is a direction of transport, okay, just as there is for mass and energy. There is also the direction of momentum itself. Momentum is a vector, okay, and therefore, there are two directions associated with the transport of momentum. One is the direction of momentum itself, the second is the direction in which momentum is transported. Okay. So, there are two directions. So, therefore, this has the flux of momentum has two fundamental directions associated with it. One is the direction of momentum, the other is the direction in which momentum is transported. Okay. And this flux of momentum, it is what is called the stress. Okay. Flux of mass was a vector. Okay. The flux of momentum is what is called a stress, and it is referred to as a second order tensor. Okay. Because it has two directions associated with it. One is the direction of momentum itself, and the second is the direction in which the momentum is transported. Okay. So, just as mass had one direction, concentration is a scalar, and you have one direction in which the direction of transport, we wrote it as Jx Ex plus Jy Ey plus Jz Ez. In a similar manner, okay, I am sorry, this should be the flux vector, J vector is equal to Jx Ex plus Jy Ey plus Jz Ez. Okay. In a similar manner, momentum is what is referred to as a second order tensor. Okay. It has two directions associated with it. Okay. So, you can write it as Ex sigma xx Ex plus Ex sigma xy Ey plus Ex sigma xz Ez plus etc. plus Ez sigma zz Ez. Two unit vectors and a component with two indices corresponding to the two unit vectors. Okay. So, in this first component sigma xx, for example, okay, this first index in our notation, okay, the convention that we will use, okay, this first one is the direction of momentum, okay, and the second one is the direction of transport. Okay. So, sigma xx means you are taking the momentum transport in the x direction. The momentum has the x in the x direction, that is transported in the x direction. Okay. Sigma xy is the momentum in the x direction which is transported in the y direction and so on. Okay. So, that is the convention that we will use. Okay. So, let me give you the formal definition. It differs slightly from mass and energy transport. Okay. Sigma ij, okay, is defined as the force per area in the I. Okay, so in the I direction acting at a surface with outward unit normal in the j direction. Okay. So, that is the definition of the momentum transport at a surface. Note that I have defined it with respect to the outward unit normal here. Okay. I defined it here with respect to the outward unit normal. Okay. That is, if I have a surface, okay, with outward unit normal n, okay, and there is some force that is exerted on the surface, okay, that force is exerted on the volume below the surface, because it is the volume below the surface, okay, it is the volume below the surface that has an outward unit normal in the n direction that is pointing upward at the surface. Okay. So, that is the formal definition of the stress. Okay. Now, this same expression I could write it in matrix form. Okay. So, the way I write it in matrix form would be E x, E y, E z. Okay. Where these refer to the direction of the momentum itself and these direction refer to the direction of the outward unit normal to the surface. Okay. So, that is the definition of the stress, force per unit area in sigma ij is force per unit area in the I direction acting at a surface whose outward unit normal is in the j direction. Okay. So, we will discuss a little bit more about the stress itself. The stress now has to be related to the gradients in the momentum, just as the mass flux was related to gradients in concentration, heat flux was related to gradients in temperature, the momentum flux has to be related to gradients in the momentum itself. How that is done we will see in the next lecture. I will continue this in the next lecture. We will see you then.